Now, I have to correct something I said last time because I said something wrong. And one student told me afterwards that it was wrong what I said. So this is also a good point to remind you that you should question everything I say. Some part of the things I say might be wrong. Okay. So just to correct it. Okay. So last time we looked at the function which is 1 over q. If we have a rational function, we have a rational number x, which is p over q, then the greatest common divisor of p and q is equal to 1. So once more, this condition is to get here a unique representation, and we also assume that q is larger than 0. So for a rational number, the function is defined like this, and for an irrational number, the function is equal to 0. Okay, so you remember this example. I considered two cases. The first case, so I have to consider, I'm interested in whether this function is continuous or not, and I'm interested in the set of points where the function is continuous. Now, because of this definition, it's quite natural that I have to consider two cases depending on whether A is a rational number or irrational number. Now, in the irrational case, last time, okay, I told you that the limit is equal to 0, which is correct, okay? And 0 is also the function value, okay? So for irrational numbers, this function will be continuous. Now, also for in the rational case, so if A is rational, the conclusion last time was correct, but there was one step which I wrote wrongly, okay? So in this case, so let's assume that A is equal to p over q, where those assumptions are satisfied. So the greatest common divisor of p and q will be equal to 1, and q will be larger than 0. Okay, I just proved that this limit is not 1 over q. Okay, that's actually what I proved. I wrote that the limit does not exist. Okay, but I haven't proved this last time. Okay, I just showed you that 1 over q is not the limit. Okay. Actually, the limit exists. This limit is also equal to 0. You just use the same argument as for the irrational case. Okay, so if this is a rational number, now, of course, for this rational number, you have here some positive function value. So let's say this one. So this is f of a. Okay. Now, if I want to prove that this limit is equal to 0, so last time I explained already why the limit cannot be 1 over q. Okay. Now, if I want to explain that the limit is equal to 0, okay, it's the usual procedure. So I have to consider an epsilon strip, and I have to find the delta. Okay. Now, you have to observe. You have to observe that, okay, so maybe I write once more what we have to do. So we have to find the delta such that if the distance between x and a is smaller, equal than delta, and larger than 0, so x not equal to a, then the distance of f of x and 0 must be smaller, equal than epsilon. Okay. Now, you see that, of course, the point A is mapped onto something which is outside of the epsilon strip, okay? But this does not matter, okay? Because the point x is equal to a is excluded anyway. Now, I just have to, because if I make now the delta smaller and smaller, okay? Of course, there is no problem for the irrational numbers, because the irrational numbers have a function value which is equal to 0 anyway. So they will be, of course, they will be mapped into the epsilon strip. Okay, so the only problem you might have is coming from rational numbers. Okay, but if you make this delta small, okay, every rational number which will still fall in this, every rational number which will still fall in this interval, okay, and is not equal to a, will have a large q. Okay, this is just the same reason as in the case where a is irrational. Okay, of course, if you get close to an irrational number, okay, if you try to find a rational number which is very close to an irrational number, okay, the q will be very large, okay? And if you try to find a rational number which is close to another rational number and not equal to this rational number, the q will be large as well, of course, okay? So this limit actually, this limit exists for all a and is equal to 0, okay? But only in this case, the limit is equal to the function value, so the function is continuous. In the other case, okay, the limit is not equal to the function value. So because last time I was just interested in the points a where the function is continuous, okay? That's why my proof last time actually was correct. There was just one step which I wrote incorrectly. Namely, I just argued that this limit is not equal to 1 over q, okay, in my argument last time, but I wrote that the limit does not exist, which is of course not true, because you have to check every number, that every number is not, is possibly not the limit, okay? Not just 1 over q. You understand what I'm talking about? Okay, so if you see that I make somewhere a mistake, okay, tell me immediately. This can happen. This will happen quite often. Now, what we want to do today is we want to look at something you have considered in high school as well, namely differentiable functions. Now, in our textbook, we have two sections which are related to this, 2.8 and 2.9. I feel they are rather the same, but I will just roughly explain what is the difference. Now, we start from the following definition. Okay, the derivative. This is section 2.8 in our textbook. The derivative of f at a is defined as, so this is here, this is the new thing which we define, namely as follows. We take the limit as h tends to 0 of f of a plus h minus f of a over h. Okay, so the derivative is just a limit, a special limit. We look at this special limit here. Of course, we can write this as the limit x tends to a, f of x minus f of a over x minus a. It's just the same. So you write here, for x you write something, you set x equal to a plus some h, then you get this definition here. Now, we will first look at an example, and then, of course, the important thing is to give a motivation why we look at this special limit, okay? But the derivative of a function, okay, is just a special limit connected to the function, okay? Of course, if it might be that this limit does not exist, okay, then the derivative will not exist. Okay, so we just look at this if the limit exists, of course. Okay, now let's look at a very easy example. Of course, you have seen this in high school, so you know already much more how to compute derivatives, but let's look at this stage. Let's look at things just from a very elementary level. So let's look at the function f of t is equal to t squared minus 6t plus minus 5. And let's say our a is equal to 2. Now, if we want to compute the derivative, so we just plug in into the definition. Okay, so we have to compute the limit as h tends to 0. Now, a plus h squared minus 6, a plus h minus 5 minus, then you have the function evaluated at 2, so which is 4 minus 12 minus 8 minus 13, so plus 13 over h. Okay, and now you, of course this is easy to handle here. You cannot use the limit laws immediately because this is 0, this would be 0, okay? So you have to do first some, you have to manipulate this expression somehow that you are able to use the limit laws. And we just do this by collecting terms. So we have here a square plus, actually, sorry, the a is given, so let's already plug in for a2. Okay, so you have 4 plus 4h plus h square minus 12 minus 6h minus 5 plus 13 over h. Okay, so this is now the limit as h tends to 0. So you see, you just collect the terms, so you have here an h square. Then you have minus 2h. Minus 2h. And then you have, okay, so this here cancels, as you see. This is something which, of course, which is expected over h. And now you see that you can cancel the h, so you have h minus 2. And now you just plug in 2, and you will get minus 2 if I haven't made a computation error. Now, you see here, this is just directly using the definition. So we see that, okay, the derivative of this function f at a is equal to 2 exists and is equal to minus 2. Okay. Now, maybe another example where the derivative does not exist. Okay, so if you look at this example, now the point we are interested in, a is equal to 0. So the question is, does the derivative of f at 0 exist? Now, we just use the definition. So the derivative of f at 0 is by definition the limit h tends to 0. Okay, so the point is 0, so we just plug in h. So we have h sine 1 over h minus the function value at 0, which is 0 over h. Okay, so we see we can cancel an h. So we have limit h tends to 0 sine of 1 over h. And this limit does not exist. Okay. So you see that the derivative of this function f at 0 does not exist. Okay, and you see also, if we would slightly change this function, okay, namely if we would change it to x squared, okay, then we could do a similar calculation with the only difference we have here h squared. Then we have here an h. And now the behavior is different. This limit here is equal to 0. Okay. The most easiest way to see this is using the squeezing theorem. Okay, so by the squeezing theorem, you see that if you look at the absolute value of h sine 1 over h, this is larger equal than 0, smaller equal than the absolute value of h. Okay, and if you now consider the limit as h tends to 0, we last time saw that this function is continuous everywhere. So here you would get 0, here you get 0, so this limit exists and is 0 as well. So in this case, for this function, the derivative of f at 0 would exist. Okay, now, as I said, the important next step, of course, is to give a motivation why we are interested in such a limit. Okay, actually, we give two motivations why we look at such an expression. One is more coming from mathematics, the other one is coming from physics. Now, the first interpretation you know already. So if you look at the function, you see that if the function looks like this from the graph, you see that, okay, there is a tangent at this point here, let's say A. Okay, so the function is y is equal to f of x. And you know that the classical problem is to find the equation of this line here, of the tangent at A, okay? We know already that the tangent, okay, has to pass to through the point A, f of A, okay? So the only problem we have is to find the slope, okay? And you know how this was solved. Namely, the idea is, okay, if we call this point here P, we fix another point Q on the graph, okay? And let's say this distance here is h. Okay, then we get secant through P and Q, okay? And from the picture you see already if the slope, so call this here slope, call this here T. So we call the slope of Tm. Then you see already from here that M should be about, okay, so you can approximate it by f of a plus h, okay, minus f of a over h. So we use the slope of the secant through P and Q to approximate the slope of the tangent, okay, which is unknown. And now the idea, the basic idea is you let h tend to 0, okay. Then you see from this picture already that the secant, okay, will eventually become the tangent, okay. So you see that the slope will be equal to the limit as h tends to 0 of f of a plus h minus f of a over h. And this is one motivation why we consider this limit. So the limit is nothing else but the slope of the tangent to the function at the point A. Okay. Now, actually, maybe you have seen this in high school. Okay, but actually, this is logically not completely correct what I'm doing here. Okay, because the first thing I have to think about is, okay, what is the tangent? Okay, how to define the tangent? Okay. Now, if you look at the picture, okay, you see, okay, what the tangent is supposed to be. Okay. But how do you define the tangent? In high school, how have you defined the tangent? You maybe say something locally. The tangent only meets the graph in one point. Okay. Locally is important because the function could be something like this here. Okay. Then you would have another point of intersection. Now this locally is not precise in a mathematical sense. Okay. So this is not a precise definition. So actually, but of course we see what the tangent is from the picture. Okay. But actually the precise way to do is to first define the derivative and then to define the tangent. Okay. Namely, once you have defined this expression, okay, you can say if this expression exists, okay, then the line which has this slope and passes through the point A, f of a, is called tangent. Okay. So you do it the other way around. Okay. So now actually having this at hand, we can define the tangent. Okay. So so the tangent is the line which passes through the point A, FA, and has slope the derivative of f at a. Okay. So, but we do not care about this. Okay. So, but actually, once more, normally you have to define first the derivative and then you define the tangent. Okay, logically. Okay. This gives a much more precise definition of the tangent. But the most important thing here is that we have an important interpretation of the derivative, namely the derivative is the tangent, okay, to the function at some point. It's the slope of the tangent to the function at some point. Okay, so this is an important first interpretation of the derivative. If we look at the function t squared minus 6t minus 5, and our a is equal to 2, then we saw that the derivative of f at 2 is equal to minus 2. So this means that the tangent to this function f at the point 2 has slope minus 2. Okay. Now, also from this tangent interpretation, we already see something which is a little bit more interesting. Namely, if you replace this here by any number, okay, because then you just move, okay. You just move the function up or down, okay? And of course, this will not change the slope of the tangent, okay? So the slope of the tangent will remain the same, okay? So you will get the same also for this function. You see this already from this tangent interpretation, okay? Now, another example is, for instance, the function f of x is equal to 2 to the x. Okay, so let's say a is equal to 0. So if we want to find the tangent to this function at a is equal to 0, okay, we have to compute the derivative, which is the limit as h tends to 0, 2 to the h minus 1 over h. Now, if you look at our limit laws, okay, I know from high school you know how to compute this limit, okay, but if you recall what we have learned in this lecture, if you look at our limit laws, okay, it will be complicated to find this limit, okay. So the only way we have at this moment, okay, later on we will discuss how to compute these limits. The only way we have at this moment is to approximate it, okay, by choosing h, which is small, to 0 and plugging in values, okay, and looking what the corresponding function value will do, okay, and doing this we will guess that the limit exists and is equal to something like this here, okay. But from the limit laws we have proved so far, okay, it is not obvious how to evaluate something like this, okay. Now this was the first interpretation of a derivative. The second interpretation is coming from physics, namely, so derivatives as rate of changes Okay, so if we do not look at any picture, okay, normally what we are interested in of course in physics, a very elementary problem is, okay, so we have some function y is equal to f of x. For instance, you could think about x is the time and y is the position of some particle, okay. Now, normally what you're interested in is, okay, if you look at some time interval, so you have if x changes from x1 to x2, then of course you have a corresponding change of y. And if we look at this interval here, we define a rate of change, average rate of change. Okay, so you look at the change of the function value, and you divide it by the change of the x value. Okay, and so this tells you something about the average rate of change over some interval, okay. But what we are frequently interested in is the so-called instantaneous change of rate, okay. Namely, you have a function, okay, and you want to have one number, okay, one real number describing, okay, what is the rate of change of the function at some point, okay, with respect to x at some point. Now, you know, for instance, if you think about this function describing the position of some particle, okay, if the function is linear, okay, you know that what you have here, this would give you the velocity, okay. But if the function is not linear, if you have a more complicated function, okay, this will give you just some approximation to the velocity at some point, okay. And you are interested in, okay, what is the velocity at this point? And this is the so-called instantaneous rate of change, which is then the limit. So you make this interval smaller and smaller. If you're interested in the point x1, you let x2 tend to x1. So x2 tends to x1 of f of x2 minus f of x1 over x2 minus x1. Okay, and this is nothing else by our definition as the derivative. Okay, so the derivative is the instantaneous rate of change of f of x with respect of x at x is equal to x1. Okay, so this is normally the interpretation you frequently encounter in physics. Okay, so for instance, if you have some function which describes you the displacement, the position of a particle which moves along a straight line. So assume at time point 0 the particle is at the origin, and then it will move along some straight line. So for instance, we are here, and this gives you the displacement from the origin at some time point. Okay, then you know that the instantaneous rate of change at some point. Okay, here is what in physics is called the velocity. Okay, and if you consider the absolute value, then this is the speed. Okay, and maybe I should call this v. And I do not give this any name. So if the function is t squared minus 6t minus 5, and we are interested in the velocity at point 2, then we saw already minus 2. Okay, which means that, so this is a kind of rate of change, okay, at this point here. So this means that if you change 2 a little bit, okay, this tells you roughly how the function value will behave, okay. It will get smaller because of the minus here, okay. Now you find in our textbook, you find several examples. Okay, so for instance, if you have a function which describes you how much coffee you can buy for some price, okay. So this gives you the amount of coffee you can buy for p euro. Okay, so if you pay p euro, you can buy so much coffee. Okay, then what is the meaning of the derivative? Okay, so this is just the rate of change of the price. Okay, the instantaneous rate of the instantaneous rate of change of the quantity was the price for some given price. Okay. Rate of change of the price of the amount you can buy with respect to the price. Okay. And for some small price changes, if the price just changes by €1, okay, you can essentially add this quantity, okay, to the derivative here to the to Q, okay, and you get what is the respective change in the amount you can buy for it, okay. Of course, from here you see already, from this interpretation, you see that normally if the price is getting higher, the amount you can buy is getting more, okay. So we expect that the derivative here, or the derivative here will be positive for all p. Okay, this is one of the examples which uses the interpretation of the derivative as a rate of change. But as you know from physics, there are many, many more. Okay, and this is an important interpretation, in particular for applications. You find also in our textbook many, many more examples, and we will do some in the assignments. Now, so just to summarize, we have two interpretations of the derivative. The first one was as a slope, which is more in the spirit of mathematics. And we have a second one, which is coming from the applications, physics or other applications, for instance, buying coffee. And there the derivative is nothing else but the instantaneous rate of change. We will later on see that those two, we will use both interpretations, and we will see that both interpretations have some advantages over the other one. So they have both some advantages. In particular, in discovering some of the basic phenomena we will prove later on. Okay, so here the only difference is that if we once more look at our definition, but now x is a variable. Okay, so we get a function here. This function is called a derivative. And f is called differentiable at a if the derivative exists. Okay. Of course, since the derivative is a function, it also has a domain. Okay, so the domain of the derivative is just a set of all x such that the derivative exists. Okay. All a where f is differentiable. Sometimes this domain, okay, the domain of f is just the same as the domain of the derivative is just the same as the domain of f, but sometimes not. Okay. Now we saw already maybe some more notation. You know apart from this notation, there are a couple more notations in use. For instance, this one is a very important one. So d over dx f of x. Okay, or if y is equal to f of x, we also write dy over dx. Okay, or sometimes we will use this notation df of f of x. Sometimes write here 1 or df of x. Everything is the same notation. Sometimes you will see this notation. D is also called d, or d is equal to d over dx is called differential operator. Okay, so you maybe also know that this notation here was invented by a German mathematician called Leibniz. Okay, and you have heard certainly in high school that this does not mean that the derivative is a fraction. Okay, because we haven't defined dy and dx. Okay, we write it as a fraction because it behaves quite often like a fraction. We will see later on many situations where the derivative actually behaves just like a fraction, but it is not a fraction because dy and dx are not defined. Okay, so of course it's not a, this is a symbol. Okay, one symbol. The reason for this symbol is because you could write the limit definition, okay, as you write here the change in y over the change in x, okay, and then you see, okay, it's kind of, you replace the limit here, you make this delta here very, very small, that's why d, okay. So you have heard this in high school, I guess. That's essentially the notation we are going to use here. Now, maybe let's look at an example. For instance, 1 over x squared. Okay, so we will later on develop quite a lot of rules. Okay, you have learned many of those rules already in high school, but at the moment, just to motivate once more the notation of derivatives. Okay, we will just stick to the definition to compute derivatives. So let's check what the derivative of this function is. So h tends to 0. Then you have 1 over x plus h squared minus 1 over x squared over h. Okay. Now we use common denominators. Okay, so we have here x plus h squared. We have here x squared. We have also an h. And we have here x squared minus x plus h squared. Now this is equal to the limit h tends to 0. Okay, now you have here x squared minus, and if you compute this, you have here x squared minus 2xh minus h squared over x plus h squared x squared h. Okay, now you get, this is the limit h tends to 0, so you can cancel out this one, which is very good because now you can cancel out the h here, which is the bad guy. So you have here x plus h squared x squared, and you have minus 2x minus h. And now eventually, now you can use the limit laws. Okay, so you can distribute the limits to the numerator and to the denominator, and we will get minus 2 over x to the cube as derivative of this function here. You see that the domain of the derivative here is the same as the domain of the original function. Maybe it's interesting to plot the graph just to see what the derivative tells us about the function. So if you plot the original function, it will look like, okay, so this is the original function. And if you plot the derivative, okay, so you will, for x positive, you get something which is negative. So this will look roughly like, and here let's maybe plot it in a different graph, because I don't have to compare it with this one. Here positive. Okay. And you see already that from this here you see some relations between the derivative. They are of course dependent, okay, because the derivative was defined via the original function. Okay, but you see, for instance, that here the derivative is negative, here the function is decreasing. Okay, here you see here is the derivative is positive, and you see that the function is increasing. Okay, we will. You have learned maybe in high school already that actually whenever the derivative is negative, you can see that the function is decreasing and so on. Okay, but we do not have yet. If you try to prove this, we do not have yet a good tool to prove something like this because we do not have a clear. We do not have a very good relationship between the function f and the derivative except the definition. And later on, one of our main goals is to derive a close relationship between the original function and the derivative. Okay, so this is one example. Now, for some functions, of course, we are not yet able to compute the derivative. We already saw 2 to the x. We are not able to compute the derivative at at the point 0, we can just use the calculator and try to approximate the limit. But of course, you can, because you have this interpretation of the derivative as a slope, okay, so of course you can directly from the function, and using this interpretation, you can find the graph of the derivative. So for instance, if we look at the function we had in the exercises, namely the cosine, the hyperbolic cosine of x, okay, then, or e to the x plus e to the minus x half, okay. You see that this function involves e to the x. We are not able at the moment, okay, to compute the derivative of e to the x because 2 to the x is also a challenge for us. So we can just use the graph and the slope interpretation to find the derivative. So you know from the exercises that this function looks a little bit like a parabola. Okay, so if we want to plot the derivative, okay, we just plot the slope at certain points. So for instance, at point 0, you see that the slope here equal to 0. Okay, so we are at 0 here. Now you see as x is getting larger and larger, okay, the slope will get larger and larger. Okay. And you see that as x is getting smaller and smaller, the slope is getting smaller and smaller and is negative. Okay. Now you could try to make a guess, okay? And you because we had in this exercise also the hyperbolic sine, okay? So the derivative of the hyperbolic cosine looks like it's the hyperbolic sine, okay? It's a little bit different to trigonometric functions because maybe in high school you have learned that the derivative of the cosine is minus the sine, okay? But the derivative of the hyperbolic cosine is this. Looks like from this here, this is the hyperbolic sine, not minus the hyperbolic sine. Okay, and you see also here, if you look at this here, if you look at this function and try just by plotting the graph, you try to find the derivative of this function. Okay, you see that. Okay, so here the derivative is okay. You do not really see it here. Okay, but you have to plot it more precisely. You will see here is 1, but the function is always increasing. Okay, you could guess. Okay, if you do this for some point, you could guess it might be this function here, which is really true. Okay, so you see for such functions, okay, because we are not able to compute yet, we are not able to compute the limits. So the only method we have to find the derivatives, okay, is by plotting the graph. Okay, and similarly, if you look at sine and you plot the graph of the derivative by choosing some points and plotting the slope of the tangent at these points, okay, you will easily get the feeling that the derivative of the sine must be the cosine and so on. Okay, let's look at another function, namely the absolute value. Okay, so the question is, okay, where does the derivative of this function exist, and what is the derivative? Now, of course, from the graph you would see, okay, that using the slope interpretation of the derivative, you would see that at 0 the derivative does not exist, okay, but everywhere else the derivative exists. But maybe let's look at it let's prove this just by looking at the definition of the derivative. So we want to find out, okay, for which x does the limit h approaches 0 of the absolute value of x plus h minus the absolute value of x over h exist. Now, it's good to, in this case, we have to divide into 3 cases. So case 1, x is larger than 0. Okay. Now, because h must be small, so choose h so small that x plus h is also larger than 0. Then you can just write this function absolute value of x plus h minus absolute value of x over h. So you can forget about the absolute values here because everything is positive. So you have the limit h tends to 0 of 1, okay, which is 1. So in this case, the limit, the derivative exists, okay, at the point x, and is equal to 1. Now, if we look at case 2, okay, so in this case, x is smaller than 0. Now you choose h such that x plus h is smaller than 0. Then we can look at the limit. Okay, everything is negative, so we can forget about the absolute value if we write a minus in front of it. So we have the limit as h tends to 0 of -1, which is equal to -1. Also here the limit exists and is equal to, also here the derivative exists and is equal to -1. And we have a third case where x is equal to 0. But in this case, we are not so lucky, because if we look at the limit, the absolute value of x over x. So let's say at the right-hand limit, then we know already this is equal to 1. And if we look at the left-hand limit, okay, this is equal to -1. So the limit does not exist. So I can also write that the derivative at 0 does not exist. Okay, so the advantage here of this method is that I do not need a picture. Okay, I just argue for which x, without relying on looking at the graph. Okay, for what x does the derivative exist? Okay, you see here also this is an example where the domain of the function and the domain of the derivative is different, because 0 is not in the domain of the derivative. And we can also, from this, we can write out now the derivative. So the derivative is 1 if x is larger than 0, and -1 if x is smaller than 0. Also from this example, you see that it makes sense to talk about right-hand derivatives and left-hand derivatives. Okay. This leads to the following definition. So let's introduce some symbol. So let's say it's called right-hand derivative of f at 0 if this limit here exists. Sorry, it should be A. And similarly, you have left-hand limit. Left-hand derivative. Okay, so for instance, if you look at this function here, this function, for this function, for instance, right-hand derivative exists, of course, for all x, okay, and is equal to 1 if x is larger or equal than 0, -1 if x is smaller than 0. Okay. Also, the left-hand derivative exists for all x, okay, but it's different from the right-hand derivative, okay. Namely, the left-hand derivative is 1 if x is larger than 0 and -1 if x is smaller or equal than 0. And of course, you have that the derivative of a function exists if and only if left and right-hand derivative of the function exists and are equal. Okay. Also from this function, because we know that this function is continuous, okay, from this function you see that continuous does not necessarily imply differentiable, okay, because this function is continuous everywhere, continuous at 0, but not differentiable at 0, okay. But the inverse is true, namely, this is the last thing for today. If f is differentiable at A, then f is continuous at A. We just saw that the inverse of this is not true. So this here is not true. Okay. But a function which is differentiable must be continuous at A. Now the proof here is not complicated, so we consider this limit f of x minus f of A. Okay. Now there is only one trick, namely you write this as limit x tends to A, then f of x minus f of A over x minus A, x minus A. Okay. And now the important thing is that we assume that that f is differentiable at A. So the limit of this here, of this part exists. The limit of this part exists as well. So we can apply the limit laws. We will discuss this in a few minutes, because also I explained this in details in the lecture. There are quite a lot of students who in the assignment, okay, use this wrongly. So if you have something like this, a product, and you want to write the limit of a product is the product of the limits, okay, it is necessary that both limits exist. Okay, so we see from this that here we have the derivative of f at A, and we have the limit as x tends to A of x minus A, which of course is 0. Okay, so you see that the limit of f of x as x tends to A is equal to f of A. But this is the definition of continuous. Okay, so here we use the assumption that the function is differentiable for this step here, and we directly obtain this here, which tells us by definition the function is continuous at A. Okay, so this finishes the proof here. And we call a function differentiable at the interval if the function is differentiable at any point of the interval. Okay, where if the interval is closed, okay, we assume that at the boundary point, okay, we replace the original limit by the original differentiability condition by this one, right hand or left hand, depending on which endpoint you consider. Okay, so if we have a function and we say this function is differentiable on the closed interval AB, we mean that the function is differentiable inside the interval. Okay, and at A the function is right differentiable, and at B the function is left differentiable. Okay, any questions? Next time we will look at some more interesting examples which can be handled already with this result here.